Okay, so let's look at an example of an RL filter. So we have an RL circuit with a resistance of 100 ohms, placed in series with a 10 Henry inductor and a 50-volt supply. And we want to know what's the steady state current if I of 0 is equal to 0 amperes. So let's start off with our source. So we know that, let's say we have some, in this case, our E of t is a constant 50 volts, with the high side and the low side here. Let's say we go into some resistor, and ultimately just be a coil, some inductor. Okay. All right. So our resistance is 100 ohms, and we have an inductance of 10 Henry. Okay, so again, if we start at some point in our circuit and we follow the current around the circuit, let's call it I, we'll pick up a potential E of t. It's positive. Go from the minus to the plus, and we'll just say by convention that we'll say that that's positive. Then we'll have a drop, so the high side on the left and low side on the right, across the resistor according to Ohm's law, which is R times I of t, and then across the inductor minus L di dt, and then we get back to our starting point and say that that equals 0. So an inductor always works by opposing a changing current. Essentially, if you use your right hand rule and you follow the direction of the current, it'll set up a magnetic field which will oppose a changing current. And since this is a DC source that we have, it's probably only going to really turn on once we flip the switch and turn the thing on, and then immediately the current should rise. So because it's clear that we're starting off with I of 0 is equal to 0, so the time at which it rises can change, whether or not you have a big, it's a really big inductance here. Typically in the micro or nano henries in most circuits, but here maybe we idealize it for the problem. So if we reorganize this problem, I get L di dt minus plus Ri is equal to E, and I'll just drop the of t convention. So I've just placed everything on one side and put the E of t or the source on the other side. So if I divide everything by L, let's see, I'll get di dt plus R over L I is equal to E over L. Okay, and so at this point we can identify our integrating factor. So it'll be E to the integral of R over L dt, and in this case R over L is constant, of course, so we just get E to the R over L t is our integrating factor. So we multiply that through, we distribute across the left hand side and multiply it on the right hand side. And let's go over here, I guess, and let's see, I'll just write the exact differential, so I am skipping steps, of, again, the function to I of t times the integrating factor, E to the R over L times t, is equal to the right hand side times that integrating factor, E to the R over L t. And if I integrate both sides, the left hand side, of course, by the first fundamental theorem of calculus, guarantees that the I of t E to the R over L t just comes out. And on the right hand side, let's see, I have E over L times the integral of E to the R over L t dt. This is a pretty simple integral. Again, I have E to the alpha t, and if I integrate E to the alpha t, I get 1 over alpha E to the alpha t. So 1 over R over L, it's going to be L over R e to the alpha R over L t, and then I'll add some arbitrary constant, and again I'll just use C sub 1 to not confuse with the capacitance, and there's no capacitor here, but just to identify it as a constant. I can use anything. I mean, I can use J's, or it doesn't really matter. So again, the L's divide out here. Let's see, I get E over R times E to the R over L t plus my C1. And so now let's go and grab this initial condition that I of 0 is equal to 0. So I have I, which is going to be 0, and times that exponential is going to be 0, equals, so this becomes E over R, and e to the 0 is just 1, plus C1, which says that my C1 is going to be a negative E over R. And so let's see, let's write this out as I of t times E to the R over L t equals, let's see, I have an E over R, just trying to gather all the stuff back together again, E to the R over L t, and C1 is a minus E over R. So let's, I guess, right over here, let's just go and solve for I of t by multiplying everything through by E to the minus R over LT. So here I'll get an E over R, and this will give me 1 if I multiply it by E to the minus R over L times T, minus E over R E to the minus R over L T. And let's see, I can factor out an E over R, and I'm left with 1 minus E to the minus R over L T. And if we recall Ohm's law, I mean, if the potential source is constant and the resistance is constant, I really get a constant current here. So, you know, this could be written as I of t is equal to, in some textbooks you may see I naught or I max. I'm just going to write it as I 1 minus E to the minus R over L T. And this is typical of what you may see in, say, a general physics book. So let's see, we're given some values, and I try to intentionally not add the values initially. I mean, I could, but this is a very general solution, given this initial condition, of course, that you have no current in the circuit. Okay, and it makes sense. I mean, if you had an open switch, unless there's energy stored in the inductor, you know, there should be no current. So let's see, we have a 100 ohm resistor, 10 Henry inductor, and a 50 volt supply. So that I, which was E over R, that's the 50 over 100, should become what, 1/2. And let me see, I have 1 minus E to the minus R over L, so I have minus 100 over 10, so it should give me a minus 10T. Okay, now this would be, I guess, the unique solution given these values, like for these passive elements and then the supply. The question asks, what's the steady state current? So if I were to write I steady state, I can get ISS. It's going to equal to the limit as t gets large of I of t. And it should be clear that if I apply the limit, this exponential term grinds down to 0, and this limit should approach half an amp, or half an ampere. If we recall the time constant from the last section, that R over L, we could write as well, we could write this exponential term as e to the minus t over tau, in which tau would be the L over R, so it would be the inverse of this R over L. Since we're going to write as t over tau, where tau would be the time constant. So L over R would be 10 over 100, or 1/10. So in 1/10 of a second, we should see the current rise 63.2%. And of course, you could have 2 time constants, 3 time constants, 4, and about 5 time constants. We pretty much say that we've approached this ISS, if you will.